what the purpose of it is. So the idea is that we've got these fractions that we talked about last time from fractional distillation, and we've separated crude oil into different fractions, which are caused by the differences in boiling points, which is linked to their carbon chain length, right? But the really key point, and the point you must get into the habit of making, is that the supply of some of those long chain hydrocarbons, such as fuel oil, which is thick and sticky and not as useful as, say, petrol, is much greater than the demand for it. And so what we do is we've got the opposite problem as well, that the supply of petrol of shorter chain hydrocarbons like petrol is less than the demand. And we've really got to get this understanding that even though this is a chemistry topic, and chemistry GCSE, we've got to talk about supply and demand in our answer, okay? So this process then is the thermal, in other words using heat, decomposition of long chain alkanes, which have fewer uses, into shorter chain alkanes, which have high demand because there's more uses, right? And we'll talk about what that looks like in a bit, but just for a second, if you can write down that we always get an alkane, like petrol, which we can use as fuel for cars, and we'll get an alkene, or possibly more than one alkene, which can be used to make polymers. So you're turning things that you can sell, or turning things that you're struggling to sell, into things that you can sell and make a lot of money from. Okay, so even though cracking is a complicated process, an expensive process, you can make very, very valuable materials from it. We always get a longer chain alkane. I've just drawn a heptane here to make it easy to draw, which is C7H16. It would always turn into, when we do cracking, a shorter chain alkane. I've picked pentane, arbitrarily somewhat. We must always get an alkene, and the alkene here, if we had 5 carbons for pentane, we must have produced a 2-carbon alkene, which is ethene. So they're the two products that you could get from the cracking of heptane. So if you just make a note of those, please. These are details which are important. So cracking can be done by heating in the presence of a catalyst, as we just did in the lab there, or tried to do in the lab. And that catalyst is we use is porcelain. So high surface area, crumbled up porcelain, and that's done at maybe 500 odd degrees, something like that. But you also have to know, and it's because we can't do this in the lab, it's often that people miss this and forget this, is that it can also be done in the presence of steam. There's a detail that I really want you to sort of not overlook. So you can use steam as well, and if you're an industrialist, you'll use both processes, and you get slightly different products if you use steam, or depending which catalyst you use. And so they choose the presence, which system they need to make the most of the thing they want to make. And that might be done at about 750 degrees, but you don't need to know these numbers, right? But in the lab, what we do, and you certainly would need to be able to write about this, certainly you'd have to label a diagram if not draw one, but I suspect you might be, you never know, you might have to be able to draw one. So you're going to draw a boiling tube, slightly angled upwards, in the lab. It's here. Is that bit? Yeah.
Lab.
Lab in the laboratory. So what we do in a science lab at school is using a sort of version of it, and you're going to have here. You're going to have your porcelain catalyst. And that's where the reaction is going to take place. You've also got down the end here, you've got some mineral wool soaked in paraffin. And for the really important thing to heat is the catalyst. There's no good heating the paraffin without heating the porcelain. So if ever you're asked to draw a diagram of this, make sure you're clear that you're heating the porcelain. And any vapours that are produced, any products of this, will be passed through the bung in a delivery tube. That end up going into an inverted test tube that's underwater. It's filled with water, it's underwater, and so bubbles of the gas produced travel through the delivery tube and end up being caught up here. So we've got the product gases up here. This is the delivery tube. This is a trough of water. And we've got a bung. We might also label that up as well. Okay. So the key point here is that the paraffin vapours pass over the hot catalyst, and that's where the reaction takes place. That's the important point. And we spoke a little while ago about suck back and what that is, but we use what's called a Bunsen valve to avoid suck back. So all it does is if you suddenly stop heating the catalyst, the gases in the boiling tube would start to cool down, contract, and water would be pulled back up the delivery tube into the really hot boiling tube, and that causes it to break, and that can be quite dangerous. But we can avoid that either by keeping heating the catalyst until we finish the collecting the gases, or we can have a little valve there to prevent it. And we can test that our products contain ethene or an alkene. And I'm going to ask you what test we can do to prove that we produce an alkene. We can test the reaction has worked, and mine didn't work because there wasn't enough paraffin, I think. But we can test the reaction has worked. We normally get about 3 test tubefuls of gas when we do this. By shaking the product gas with bromine water, if cracking has taken place, you end up getting an alkene, and alkenes, of course, in bromine water go from orange to colours. There's lots here expected to know. All right. So, really, I mean, we've had to rush a little bit because of all the in and out business that's been going on. But I want us to be able to write the kind of equation that you might have to write here. So I'm going to write some equations down. You're going to see, if you, like we did on the board, but you're going to see if you can figure out what the other product is in each case. So example reactions, this is exactly the kind of thing you'd be asked. So if we've got, say, C10, H22, and if I told you that one of the products is C7H16, you should be able to work out what the product alkene is, just by doing a little bit of very simple maths. We'll check it together in a sec. If I told you we started with something like C18H question mark, I want you to tell me what the question mark would be. And if we do cracking on it, we might get C12H something, and C, and then something else. So let's see if you can fill in those blanks. Question 3, we had C12H26. It's a slightly unusual question, this, because you can get two alkenes formed, two different alkenes. Sometimes this is two of the same alkene. It was 2C3H6. So what would the alkane be? Question mark. And the last one we'll do as a word equation. Octane might turn into hexane. What would the other product be, please? You can think about those and we'll work through them in a sec. Just to wrap up then, the very, very common questions in GCSE about this topic, you will have to know the idea about supply and demand and the process and the conditions and everything, even draw and label the diagram. But you would also very often get a question like this where you have to work out what the products are. Anyone missed out on their test score, hang back at the end and I'll tell you what it was. Thanks everyone.